In this video, we're going to use food additive safety assessment to demonstrate the 4 parts of a risk assessment. Let's begin with a word or two about food additives. Food additives are chemicals that are intentionally added to our food to preserve the food, to add nutrition, to enhance flavor, to provide color, texture, or for other reasons. There are many thousands of food additives now, and before a food additive can be used, it must be thoroughly analyzed. It will be safe for consumers. Safety is different from risk. Food safety is defined as you see here. It's experts' best judgment about the level of exposure to a substance that has reasonable certainty of no harm to humans under the intended conditions of its use. That's not science. Best judgment, reasonable certainty, intended conditions of use, these are all assumptions built into the definition that are essential for the definition of food safety that's used by our U.S. government agencies. Here's your short course in food additive safety analysis. The risk is ultimately going to be characterized by this ratio that you're looking at here. If the amount of the substance consumed, that is the EDI, estimated daily intake, is bigger than the safe amount of the substance, that is the acceptable daily intake, then the consumption level is not safe. If the EDI is smaller than the ADI, that's considered safe. And if the EDI and the ADI happen to be equal to one another, that would also be considered safe. Now let's take a look at what goes into generating this ratio. In this slide you see the steps in a food additive safety assessment. What you don't see is hazard identification. Risk managers or someone else, presumably a company that was proposing to use a new food additive that they had invented or discovered, would identify the hazard. So hazard identification is not shown here. If we take a look at bullet number 1, 2, 3, and 4, these are all part of hazard characterization. Bullet 5 is the exposure assessment. And the final bullet is the risk characterization. So over the next couple of slides, I'm going to step you through each one of these so you can see how it's done. Let's take a look at this process schematically. Notice our graph here. On the horizontal axis, we have dose, and it's measured in milligrams per kilogram of body weight every day over a lifetime. You're going to see 2 values on this horizontal axis, the ADI, the acceptable daily intake, and the NOAL, the no observed adverse effect level. We're going to imagine that we have a product that has a no observed adverse effect level, hold on, I'll define it soon, of 5 milligrams per kilogram daily for a lifetime. This number is basically the largest dose of the additive that can be given to animals without causing any adverse health effects. So we have a purportedly or potentially safe level for animals. The problem is the animals are given very high doses of the chemical, and humans will typically be consuming small doses, and they are not animals, they're humans. So we have a substantial extrapolation issue. The extrapolation is handled by the safety factor that you have there. If you divide the NOAL by the safety factor, you obtain the ADI. Lifetime doses above the ADI are considered less safe than lifetime doses below the ADI. So let's consider all this with a simple example. We're going to use boric acid. That's an indirect food additive. That means it's not directly added to the food for color or nutrition or flavor, but it indirectly gets into the food. In this case, it migrates from the packaging of the food. Boric acid is a color stabilizer that's used during the manufacturing of packaging materials. So there is this potential for migration of boric acid from the packaging material into the food. And that's what we're going to be investigating in this example. So boric acid has been identified as the hazard of concern. Now we're going to begin to characterize the hazard. We're looking at the adverse health effects associated with this particular hazard. If you recall a couple of slides back, one of the first steps was to gather the evidence, to do the toxicological studies that are needed to determine the extent to which the additive that we're considering presents a risk to humans. Well, typically that happens in animal studies. A relatively high dose of the chemical is given to relatively few animals, maybe to 32 mice or rats. A very high dose is given. And if that high dose kills any of the animals, we know that it can be lethal. So if it would, for example, kill some animals, what we have to do is back off of that high dose and give them a lower dose and see what happens. If no animals die, that's not evidence of no adverse health effects. So typically what happens is once you have found a suitably low dose that doesn't cause deaths, you would give it to the mice or the rats for their entire lifetime. And then at the end of their lifetime, you would examine the animals to see if there were any cancerous tumors or other kinds of health effects. The problem with animal studies is usually you don't give these animals low doses. We're giving them high doses because we're looking for trying to force those adverse health effects. So as I mentioned before, there's a substantial extrapolation problem from animals who consume high doses to humans who consume low doses. And there are two ways that this is done in the food safety community. One of them is dose response curves, which we're not going to cover here today. And the other is the acceptable daily intake, which we will cover. What we're looking for in these animal studies is the NOAL, the no observed adverse effect level. And as you see here, it's defined as the biggest dose of the chemical that produces no toxicity, no adverse health effects. And that would be measured in milligrams per kilogram of body weight daily for a lifetime. This extrapolation problem that we've talked about has several different approaches. I mentioned dose response curves, and with dose response curves there are many mathematical models possible. That's one of the reasons we're going to skip that for now. An alternative approach, and one that is used in the food safety community rather extensively, is to use safety factors or uncertainty factors to account for this extrapolation problem. Bear in mind that if we're talking about risk assessment, we are now in what the Red Book calls the hazard characterization. We are now in what your textbook would call the consequence assessment. But what we're looking at is this idea of safety factors, or as they're sometimes called, uncertainty factors. This is one way that the food safety community deals with the uncertainty in going from high doses in animals to low doses in humans. What you would do is identify all the factors that pertain to your food safety assessment, and you would combine them by multiplying to get an overall safety factor. So for example, going from animals to humans is a factor of 10. Going from high doses to low doses is a factor of 10. And the variability among humans, their sensitivity to this chemical, might be a factor of 10. So if I've identified 3 uncertainty factors, I would multiply them 10 times 10 times 10 to obtain an overall safety factor of 1,000. The ADI is obtained by dividing the NOAL, which is indeed the result of rigorous toxicological studies, so that is a good bit of scientific evidence, and we divide it by a safety factor. that is not so scientific. So this is one of the reasons that we say risk assessment is science-based. It's not pure science, and that's because we have uncertainties that bedevil us and keep us from dealing with pure evidence in all of our assessments. So let's return to our boric acid example. Reviewers went through the literature in toxicology, and they found several studies that were done with 2,500 parts per million and 3,000 parts per million, but they revealed that they did indeed have some adverse effects with them. So those studies didn't reveal a no AL. The reviewers looked at the studies that were available, looked at the effects that resulted from the doses administered, and they made a judgment that 1,000 parts per million was a reasonable no AL. There were no cancerous health effects at this dose. There were some non-cancer effects, but they were generally considered to be insignificant, relatively insignificant. The safety factor that they used with this was 1,000, and that's because of extrapolation from animal to humans was a factor of 10, variability among humans was a factor of 10, and because the non-cancer effects were reproductive effects, they used a factor of 10. Dividing a NOAL of 1,000 parts per million by a factor of safety of 1,000 produces the ADI. That's the maximum acceptable daily intake, and it's not an absolute limit that can never be exceeded. There may be days or instances where a person's consumption of a chemical will exceed the ADI, and that does not mean that they will necessarily have an adverse health effect. The ADI is an estimate of the amount of an additive that can be consumed every day for a lifetime without adverse effects. It's used to estimate population safety. It's not a very useful measure for individual safety. So we can say that in general, a population of people who stay below the ADI will be okay. But if we pick one individual who might be highly sensitive or have a predisposition toward cancer, we can't say anything about that one particular individual. So let's take a look at what we have now. On the horizontal axis, we have a dose. On the vertical axis, we have unspecified non-cancer health effects. But what's important is the breakpoint that is provided by the ADI. So we found that 1,000 parts per million resulted in no observed adverse effects, but to get from animals to humans, we divide that number by 1,000 to obtain an ADI of 1 part per million. So if this person consumes boric acid, where the boric acid is 1 part per million of their diet per day for a lifetime or less, that is considered safe. If it is more than 1 part per million, that is considered unsafe. So this would conclude the hazard characterization. We have basically said that if you consume more than 1 part per million per day for a lifetime, you could expect to have adverse non-cancer health effects. Now we need to turn to that exposure assessment, or as your textbook would call it, the likelihood assessment. The Food and Drug Administration's Center for Food Safety and Applied Nutrition looked at all the foods that had boric acid used in the packaging, where the packaging came in direct contact with the food. Then they made an assumption of 100% migration of all that boric acid into the food. When they use that assumption and the food intake diets that they have, they collect a great deal of information on what kinds of foods people eat, with what frequency and in what quantities. So this is basically how much of the boric acid is in the food times how much of the food people eat, and add that up for all the foods that might have boric acid. And they came up with an estimated daily intake, an exposure assessment of 1.2 parts per million daily for a lifetime. This completes the exposure assessment. Although it's one slide and didn't take us long to describe, it can take a substantial amount of laboratory work to establish this value. So here's a typical risk characterization for a food additive safety assessment. Using the EDI and the ADI that we've calculated, we use that ratio that you saw earlier, 1.2 parts per million divided by 1 part per million is equal to 1.2. That's bigger than 1, so this chemical is considered to be available in quantities that are not safe. Risk management hopefully follows the risk assessment, and in this case, the Center for Food Safety and Applied Nutrition required industry to change one aspect of the manufacturing process by including a washing step to remove any residual boric acid, thereby lowering the EDI. Now, industry would have had the option to have contested the assumption of 100% migration. That was an assumption without evidence. So industry could have undertaken studies to show what the actual migration rates were. Those kinds of studies are not cheap, and in this case industry decided that it was better just to add this washing step than it was to try to contest the assumption of 100% migration. So what you've seen in this video is just a simple application of the 4 steps that we're talking about. Just about every field of application of risk assessment uses some version of these steps. They don't always call them by the same name. The Red Book talks about hazard identification, dose response, exposure assessment, and risk characterization. The idea of dose response was later changed to hazard characterization. So food safety tends to use hazard identification, hazard characterization, exposure assessment, and risk characterization. In your textbook you have a generalized form of this so that you would have steps that would be applied not just to food safety but to virtually any application of the risk assessment process.